Okay, today we are going to learn about how to use a switch network to realize the buck conversion of a DC voltage source. So we'll start a buck converter and its small ripple approximation. So first, let's look at how to derive a buck converter. So we can first plot the input source as DC source VG, and we connect a switch network which is a single pole double throw switch. So we have pole position 1 and pole position 2. So for this switch network, we have its output as Vs. By controlling the switch pattern of this switch network, we can realize a specific waveform for Vs. So basically, this circuit contains two operation modes. So for operation mode 1, so we attach this switch to position 1. And this mode happens from 0 to DTS. So correspondingly, we can plot the voltage waveform for Vs over time. So in operation mode 1, because switch is attached to here, so we will have the Vs equals to the input voltage. And this duration is from 0 to dTs. And then we will have mode 2. So in mode 2, we attach the switch to position 2. So mode 2 happens from DTS to TS. So correspondingly, we can also construct the voltage waveform for VST in mode 2, because this switch is attached to here, so the Vs is shorted, so the voltage here becomes 0. And this point is TS. Yes. So from those description, we can see that there are two major variables or parameters. One is called the TS. TS is called the switching period. Switching period means that this pattern is repeating periodically. So we'll have this square wave repeating like this. And based on the switching period, we can also introduce a parameter which is Fs, which is the switching frequency. So this quantity equals to 1 over Ts. So we call this as switching frequency. And another parameter will be D, which is the duty cycle of the converter. So this means that the proportion of operation mode 1 counts D parts of the entire switching period. So equals to the operation mode 1's duration over one entire switching period. Okay, so that's the key parameters for the buck converter. So based on this waveform we obtained from the switching network, we can see that this is a square wave, right? Square wave. And based on this square wave, we can extract its DC component. Which will be the average of Vs. So for the average value will be equals to the integral of the Vs over one switching period divided by the length of this switching period. So 1 over Ts integral of Vs from 0 to Ts. For this integral, it is easy to derive. It is equal to the area of this rectangular, right? So we just use the high school math to calculate. So the integral equals to base times height. So the t cancels here. So this will be equals to dVg, right? dVg. So this means that the average DC component for the output switch network will be a bucked voltage, right? D times Vg. So the next step, we are curious about that. How can we extract such a DC component? So the answer is that we can install a low pass filter circuit to remove the harmonics and parse only the DC component. Pass only the DC component, we can get a DC quantity here. So next, let me show you how we can construct this circuit with the low-pass filter network. So let's use the red pencil, red chalk here. So same, the left-hand side is input voltage. Switch network. And on the right-hand side, we plot a LC filter network. Here is an inductor L. Here is a capacitor C. And on the right, we have the load resistor R. So basically, this is a low-pass filter network. And on top of this circuit, we can mark several quantities, like we can mark the Vs, and we can mark the inductor current IL, and also we can mark the capacitor current IC, as well as the output voltage V. So those quantities are time varying, right? So T. So after this low-pass filter network, the Vt will be approximately equal to the input of the filter, low-pass filter network, equals to the average, right, due to the filtering effect. So we can see that the average equals to dVg. So this equation shows the relationship between the input voltage and output voltage. So we can plot this relationship graphically. So x-axis is the duty ratio, y-axis is the output voltage. So duty ratio should be in the region from 0 to 1. And based on this equation, we can see that the output voltage rises linearly with the increase of D. And ideally, when the D reaches 1, so this output voltage equals to Vg. So that's the output characteristics of buck converter. So we can see that its voltage conversion ratio we denote this voltage conversion ratio as M. M is a function of duty cycle. And it equals to the output voltage divided by input voltage. So we insert output voltage to here. So we can see that for buck converter, its voltage conversion ratio equals to its duty cycle. So very simple, right? Very effective. We can realize the DC to DC voltage step-down conversion using this simple circuit. And next, we are going to look at an important principle in the power electronic analysis, which is called the small ripple approximation. So we usually refer to the capacitor voltage. For example, for buck converter, if we look at the capacitor voltage, if you use an oscilloscope to observe this capacitor voltage, you will see such a waveform. So in time domain, here is the output voltage. So usually for DC converter, the output voltage will be like this. So on top of a DC bias, we mark as capital V. There is a small signal variations on top of this DC bias. So that is the real world signal you will observe when you take measurement using a oscilloscope. So based on such a feature, so we can introduce the naming system for those quantities. Like we use Vt to represent the full signal. The full signal contains two parts. One part is the DC bias, which is DC component. And on top of it, there is a ripple. So you'll see that I use capital letter to denote the DC component and use the lowercase letter to denote the small signal AC. So this is small signal AC ripple. So typically, for a well-designed DC converter, we will have the DC bias much bigger than the amplitude of the ripple. So we call this as small ripple approximation. So this can be utilized in our circuit analysis to simplify the theoretical derivation. Okay, so based on this subsection, we can see that Bach circuit is such a circuit which utilizes a single pole double throw switch and energy storage units to realize the voltage step down conversion. And practically, we can utilize two semiconductor power devices to implement this single pole double throw switch. And in order to simplify the analysis, we usually ignore the small signal AC ripple of the output voltage. So we call this principle as small ripple approximation.